All right, so welcome back. Welcome to a new week. Let's start by going over the overall plot of what we're trying to do here. So, what's the idea? So we are imagining we have some partial model of some population that we're trying to understand. So our partial model might be something like we know the fact that our probability distribution that describes the population is given by, for example, exponential distribution, but where lambda is unknown. Or maybe it means that we are given by some normal distribution. So 2 pi sigma squared e to the minus half of x minus mu squared over sigma squared. But again, where mu and sigma squared are unknown. So more generally, we imagine that our function is of the form, f of x is some f depending on some unknown parameter theta of x. And, we'll be flexible about how we notate that. It's conventional to write that as x semicolon theta. But, really, if you think about, this expression, these expressions that we have like lambda e to the minus x, for example, then if we want, we can think of it as a function of two variables, as a function of x and lambda. Of course, these variables have different roles. When lambda is specified as having a given value, what we get is a distribution, and x is the variable for that distribution. But nonetheless, formally, it's just a function of two variables. So we can really write it in all three of these kind of ways, or however we want, and different perspectives would be useful as we go. So in any case, so this is what we start with. We start with a partial model with some unknown parameters. And what are we trying to do? We are trying to make a series of observations which will allow us to estimate these unknown parameters, sigma, or maybe we have some, theta, or maybe we have some various thetas. In the case of the normal distribution, we have two of them. And these estimates let us then pin down our model with a higher degree of confidence. So we get a more specific model, or at least more confidence in our parameters, some estimates with some degree of confidence in our parameters, some confidence intervals describing the value of these thetas, and that gives us a more specific model on which we can then make subsequent predictions. All right. So, of course, this question is how do we do that? And that's what this course is really about in some sense, at least for a good chunk, right? So, so far, what have we talked about? We've talked about, what have we talked about? We've said if somebody gives us some actual estimator, then we've described ways in which we can describe, like, how good that estimator is. Is it unbiased? Is it asymptotically unbiased, at least? Is it efficient? Is it consistent? Is it sufficient? These are all kind of valuations on how good that estimator is, how well it performs in different ways. But there's this question of how do we actually find these estimators in the first place? So, so we have some specific examples, such as if we're trying to understand the population mean, we have been using this estimator, which is the sample mean. If we're trying to understand the population variance, then we've been using the sample variance. But what if we have now some, I don't know, have we talked about the exponential population so much? Like if you have an exponential population, how do you estimate this value of lambda? Or whatever other kind of distribution we might have. We should have a general procedure, if we'd like, for describing how to get these estimators. So we want, general procedures which take some general form of our distribution with unknown parameters, and which will then output some estimators. So this week we're going to talk about two specific ways of doing that. First, we're going to describe what's called the method of moments. And then subsequently we'll talk about the method of maximum likelihood. All right, and so that's what's on the menu, and that's what's coming up.